pleasure to introduce Gautam. He's currently at MIT and will be spending time of science the next year.
Thank you, Luke, and thank you to all the organizers for organizing this workshop. It's been a lot of fun. I've really enjoyed it. And yeah, so the topic of this workshop is modern challenges in learning theory. And I decided to make my talk on one of my favorite modern challenges in learning theory, which is that of robustness. At a very broad, in a broad sense, robustness asks, how can we ensure that modern machine learning systems are prepared for when the real world doesn't match our models? Of course, this is very general, so let me try to elaborate on this. And in some sense, I lied. While it's a modern challenge, it's also been a very classical problem. Let me start with a bit of classical motivation behind this type of problem. And like I said, it's roughly for model misspecification, when the real world does not match our models that we create. So to provide you with one example, we often like to think as data which comes from nature is a Gaussian distribution. This is very mathematically convenient for us. But I claim that nature by itself almost never samples from a Gaussian. Frequently, we use the Gaussian as a model because we're adding together a bunch of things, and by CLT this converges to a Gaussian, but it's not exactly a Gaussian. So there's some slight mismatch there. Also, whenever we're doing any sort of hypothesis test, whenever we're gathering data, perhaps, we're not really going to have IID samples, for example. There's going to be some correlation somehow, which maybe we have to account for. And a final, perhaps classical motivation is dirty data sets, in the sense that, you go out into the wild, you're measuring something in nature, but sometimes you make mistakes. It's a 6, you write down a 9 instead. Sometimes your equipment malfunctions. Or perhaps you're gathering data from a bunch of different people. You have a consortium of different sources, and they each feed you data, but there's some slight inconsistencies behind how they report their data. So I've been told by my friends in computational biology that this is actually a real source of error, and we need to be robust in that type of setting. So again, these are some of the more classical, perhaps, areas where people want robustness. But of course, nowadays, it's been more of a focus in terms of data poisoning and adversarial attacks. So let me show you a picture I'm sure many of you have seen before, this one. It's been found that current machine learning systems are surprisingly brittle in many cases. So take a look here. On the left, we have a picture that is classified by a modern neural network as a panda with 57.7% confidence. But if you add an imperceptible amount of malicious noise, then you can see that the same neural network classified as a given with 99% confidence. So this is kind of fun. You see, like a panda turns into a given, very neat and cute. But you might be wondering, what does this have to do with anything that's meaningful? Like, okay, so we have a classifier, we make a few mistakes, that's fine. But I claim that these type of things come up in situations where we really need reliable machine learning systems, things which will not fail. And to provide you an example, here's another paper, another result, where this involves something which may be more security critical. So you can see at the top, what the researchers did was they took a bunch of pictures of stop signs, and then they just planted some watermarks or backboards on them. So you can see here's a stop sign with a yellow square, here's a stop sign with a flower. Just some very innocuous changes to it. But then they told the classifier, they poisoned the data set, saying that, oh, this is a stop sign. This in particular is a speed limit sign, for example. And so by training on a poisoned data set like this, they're able to have a real classifier make it think that this stop sign is actually a speed limit sign with 95% confidence. So you can see that they put a real physical sticker on this, and that can fool an image classifier. So you can imagine if you have a self-driving car, this is the type of situation which you really do not want to be incorrect in. And yes?
In this example, the classifier needs to be trained maliciously.
Precisely. This is a poison data attack, which is more the setting I'll be focused on in this talk. But yeah, often classifiers are trained, by looking up just a collection of images, maybe online. We don't really have any formal guarantees about where this image came from. Suppose you just look at all images on Flickr and try to train something like that. You can imagine maybe one user is just putting up Flickr images which are intentionally mislabeled. And in that case, you might be training on bad data. So just one more motivation I want to show you, an ambitious move try to play the video. Will this work? Yes, great. So this is actually a 3D printed turtle. Take a look at this 3D printed turtle. It is classified as a turtle by Google's Inception classifier. But take a look at this 3D printed turtle, which is synthesized to fool a state-of-the-art image classifier into thinking it's a rifle. And the really, really cool thing about this is from almost every angle, it still thinks it's the rifle. So this is kind of fanciful and cute, but imagine if it were the other way around. Suppose you had an automated security checkpoint which thought that a 3D printed rifle was a turtle. What I'm trying to get at here is that robustness is critical, and we really want to develop algorithms which are provably robust worst-case noise. Worst case is especially important in the setting of adversarial attacks.
You know, this is more scary than the example you gave. If a drone was thinking that I'm a rifle, it would shoot me.
Sure, yeah, that's exactly. I guess potentially if it were trained with poison data, yeah, that's the risk.
But the Russians would be.
So yeah, today I'm going to tell you about provably robust and effective algorithms for parameter estimation and fundamental supervised learning tasks. I'm going to focus mostly on the first part, but I'll tell you how these things can be applied for the second part towards the end of the talk. And so for the first part, I'm going to tell you about robust high-dimensional parameter estimation. This is with a cast of excellent co-authors, including Elias, who's a professor at USC, Daniel Kane, who's a professor at UCSD, Jerry, who's a grad student at MIT, but will be starting at MSR Redmond, Ankur, who's a professor at MIT, and Alistair, who's between postdocs at USC and Stanford right now. So let's start with a problem hopefully you're all familiar with, a classic parameter estimation problem. Suppose you have samples from a Gaussian distribution just in one dimension. Can you estimate its mean and variance? And of course, as many of you know, yeah, you can very easily. You just take the empirical mean and variance. And these will converge to the true mean and variance. All right, that's it, talk's done. No, I promised you robustness. So we want to investigate this problem in a robust setting. So now we're given corrupted samples from the 1D Gaussian, something kind of like this. You have a true ideal model, which is indeed a Gaussian, but then there's some sort of corruption, which I'll explain in a sec. And then you have an observed model, which is not quite Gaussian. Can we estimate the parameters of the true ideal model? And let me emphasize, let me actually explain what the corruption model is. We're going to use a very adversarial corruption model, where an adversary moves an epsilon fraction of the data set arbitrarily. So to illustrate this, we have some clean samples like this, but then we have a very powerful adversary who comes along and moves a fraction of your data set. So you can see these red samples, they were originally on the left, but he's moved them over to the right, which you can imagine will shift the parameters a bit. For example, the empirical mean will be shifted a bit to the right, etc. So this is the type of noise model. I hope this is clear. If there's any questions, feel free to ask. This is what we're going to be working with for most of the talk. Good. So now let me formalize the problem statement. We're given an epsilon corrupted set of samples from a univariate Gaussian canal, and we want to efficiently find parameters mu hat and sigma squared hat, which have a guarantee that the true model and the model we return is O of epsilon in total variation distance. Let me make 2 comments on this. First of all, the best possible error in this corruption model that I've described is epsilon, 1 times epsilon. So we'd ideally like to be competitive with that. And the one thing I've not mentioned here, suspiciously, is that I didn't mention sample complexity. I think sample complexity in this talk will only complicate things. I'm just going to say now that pretty much everything we get is highly sample efficient, near optimal, except in some cases, but just to avoid confusion, I'm going to sweep this under the rug. Good. So this is the problem statement. And the first question you might ask is, do the empirical mean and variance work? Is everything still fine? And you'll pretty quickly find that no, which you can see by considering this example. Just by moving a single point off to, say, positive infinity, you can see that the empirical mean will be shifted by an arbitrary amount, and the empirical variance will also be shifted. So this is an example of what statisticians like to call an estimator with a very low breakdown point. Just by moving one sample, you'll have a very corrupt estimate.
You have to move it really a lot.
Yes, yes, but I guess there's another model you can work in with, say, bound and noise per point, but we're working sort of the gross corruption model. That said, you might think this is kind of silly thing, because you have, 1 point way out. There's some natural things that you can do.
In fact, statistically, this doesn't work.
I'm sorry?
Because if you, the extremes of the Gaussian cannot be bigger than square root log n. So if you put something at distance n, you detect it instantaneously.
Precisely. So for these sort of naive, very gross corruptions, one thing you can do is just a naive pruning. Basically, if one point is sufficiently far away from every other point, then you can prune it and you'll be okay. So that's an example of a statistic that will work in low dimensions. In fact, there's other statistics that work in low dimensions. The one I'm going to mention for now are the fact that the median and the interquartile range work. In particular, you can use the median as a proxy for the mean, and the IQR as a proxy for standard deviation. This provides a picture, I guess you probably look familiar. This is the median, which is the middle. But the IQR is the difference between the 25th and 75th percentiles, which is a good estimate of the scale of the distribution. If you appropriately rescale it, then this will be a good proxy for the standard deviation. So formally, we have the following theorem. Given an epsilon profit set of samples, let mu hat be the median and sigma hat be a rescaled IQR for the data set. Then you can get the L1 distance is small between the two distributions. If you do that, yep.
But then you really need the Gaussian, right? To be able to go from median to mean.
Yeah. For many sorts of distributions for many sort of distributions, the median will be a reasonable thing as long as not, say, like supervised modal or something like that. As long as it behaves nicely around the 50th percentile of your data set. So yeah, most natural classes you can think of will have a problem.
So regarding our estimation of mu hat and sigma hat is it optimal?
I'm sorry?
If you want to estimate mu hat, for instance, imagine you know sigma, it's not optimal.
This, I think, is optimal up to constant factors. You're saying, sorry, if you know...
So imagine even if you know sigma, is this method optimal for estimating mu hat?
Yeah, I'm pretty sure this is optimal up to constant
I
factors.
think it's a maximum likelihood estimate for the median as the mu.
These are some results which
Yes.
They were proved by Hoover in 64 that the median minimized this.
not for any
Right,
experiment.
this is a very classic result.
But if epsilon is very small,
In very small regime, then I think it should even give a better estimate because the CDF is very well
it's
behaved.
not optimal.
Maybe we can chat about this more offline. But at least in this case, it will give you something which is over epsilon accurate. So this is the one-dimensional case, which I think is fairly well understood, even up to constant factors for certain estimators, at least. But this is just a one-dimensional case. I want to understand the higher-dimensional case, which is more common in modern data settings. So say if we're in 100 dimensions. Let's ask the exact same question now. Given an epsilon corrupted set of samples from a d-dimensional Gaussian, we want to efficiently find parameters mu hat and sigma hat such that the L1 distance is small. The same thing, but in higher dimensions. And for now, just for the presentation, I'm going to focus on the case where we know the covariance, say it's the identity, and we just want to estimate the mean. In particular, we want to find an estimate of the mean, which is accurate in L2 distance up to O epsilon. So this is a bit simpler, but I claim we can do the more general problem. But for now, let's focus on this. Right. So mean estimation. In one dimension, what would we have done? We would have just taken the mean and we would have done something that's robust. So the natural question to wonder is there a type of median which would be effective in higher dimensions? So of course, this was asked a while ago, and the statisticians in 75, Tukey in particular, came up with a concept which we call the Tukey median. This is good because it is very accurate, but the bad part about this is it's empty hard in general to compute on high-dimensional data sets. So let's just take a look at what the Tukey median is. This is the definition of first we have the Tukey depth of a point. The Tukey depth looks at the minimum number of data points on one side of a hyperplane through the point. So in other words, you sort of inspect every single hyperplane that could go through a point, and find the one that minimizes the number of data points on one side. Kind of, if you wanted to dig yourself out of the data set, what's the minimum number of data points you'd have to pass? So that's the 2p depth of just a single point. And then the 2p median of the data set finds the maximum depth over the entire space, not even necessarily a point in the data set. So you can see that just by reading this, it's not quite clear how to compute this efficiently. But it's well defined, in fact, and for the time being, I think people are satisfied, especially in low dimensional settings. So that's one thing, but of course, computer scientists care a bit more about doing things computationally efficiently. So an alternative definition of the median is the geometric median. This thing can be computed near linear time due to a result of Cohen et al. Just a few years ago. But the error guarantee you can see here is that we get something that's epsilon times the square root of the dimension. So you can imagine if we're in very high dimensions, hundreds or thousands or millions, then for reasonable values of epsilon, this will give you vacuous guarantees. So in this case, we have something which is fast, but not accurate. And just in case you're not familiar with geometric median, I want to say it's the point which minimizes the sum of the L2 distances from the other points, which can be compared with mean, which just computes the sum of the L2 distances squared.
So even if there's no corruption, the best thing you can do is something as square root of b over n, right? So I guess you're assuming that epsilon is bigger than that.
Yeah. We're sort of assuming that generally you can think of epsilon as being a small constant, like 0.01 or 0.1. 0.1 might be a lot, but yeah, generally a small constant. It's the regime we're focused on. So yeah, you can see how the geometric median looks immediately much more computational than the 2p median. But unfortunately, while it has some robustness properties, including a very high breakdown point, it does not have the error guarantee we want. And you'll see this goes on. A similar method that we sort of talked about before, naive pruning, is of course very efficient, but you're going to lose a dimension-dependent factor. And then there's another method, a tournament-based approach, using sort of Shefe estimators, will give you something which is accurate, but unfortunately, you're going to need to consider exponentially many hypotheses, so it's slow. And the list goes on. But the main point I'm trying to get at here is the fact that every estimator which has been known before is either slow, hard to compute, or is inaccurate. So this raises the question, can we get something which avoids both of these pitfalls? Is computationally efficient robust estimation possible in higher dimensions without falling into one of the two traps of computational tractability or accuracy which depends on the dimension? And our main result is that we get the first result, which is both accurate and efficient in high dimensions. This is one work with the co-author I mentioned before, which appeared at FOSS a few years ago. And just to give you a flavor of the theorem statements, again, for now, I'm just telling you about the ones which have known covariance. But given a corrupted set of samples, there exists an efficient algorithm to compute mu hat, such that the L1 distance between the unknown distribution and the one with this mean we can compute is O of epsilon times square root log 1 over epsilon. And like I said, equivalently, we're estimating the mean in an L2 distance. Yes?
Just one question, because you know the covariance matrix, can you use it somehow to detect which points you will make?
Yeah, that's sort of where the algorithm will come in. We're kind of going to have to look at the covariance matrix in order to figure out where the corrupted points are really grouped. And use similar things if we don't know the covariance, we can do things for the higher moments, but I'll touch on that a bit later.
So here the historian thing can do whatever they want.
Absolutely anything with the restriction that they can only touch epsilon times n of the points.
Is the log term necessary?
Very good question. And this is a weird thing that in some models it is, in some models it isn't. Yes, there's a computational lower bound for the SQ model in the model described so far. So basically, if you want to get rid of this log factor, this is computationally hard in high dimensions, we believe. Like, it's proven formally for a specific computational model, but in general it's unclear, but we believe it's hard. But if you look at a model where the adversary can only add points and not subtract them, then you can get rid of the log factors, which we did in another paper, which I'll mention. So I'll touch on this again a bit later. Yes?
If you didn't know that they are Gaussian and you just want to estimate the mean with corruption, can you still do it?
That's an excellent question. Yeah, because you might think Gaussian is a very strong assumption. We can also do estimation in, say, when we have weaker moment conditions. For example, if you just have bounded second moment, you can still do some estimation, but of course it'll be worse than this just because you don't have as tight control over the details. So yeah, these are all very good questions. I think they'll revisit again later in this talk. So good. This is our bound here, and I guess I just really want to emphasize the things which I like about this bound. First is polynomial time, and it simultaneously has no dimension-dependent factor in the error, in the accuracy. I'll just mention that there was also, just to show that this was something else that other people were also interested in, there's a concurrent and independent work by Lai, Round, and Paulo, which also appeared in the same conference, which focuses on the same type of problem. They have different algorithms with slightly different guarantees. They have, for example, a dependence on the dimension, which is logarithmic, which is very good, but we managed to get rid of that. Cool. So now I want to spend the next part of the talk trying to describe to you what the challenges in this are and how we overcome them. So why do naive methods get stuck? Consider the following simple algorithm, which we've discussed a bit before. Just look at your data set, remove all points which are obviously too far to be from the Gaussian, and then take the empirical mean of the remaining points. So this is well defined, except what does obviously too far mean? So let's delve a bit deeper into this. How far is too far? So I'm going to just say a very simple fact about a Gaussian in one dimension. This would be just by looking at the PDF, you get this. The probability that a sample differs, deviates from the mean more than square root log 1 over epsilon is O of epsilon. Just to pictorially illustrate, you can see if you chop off the tail at this point, you're going to only remove O of epsilon mass. So this leads to the following simple algorithm. Just truncate your data set, truncate any point which is root log 1 over epsilon away from any other point. This has the following two guarantees. Look at the good points, that is those which were truly from the Gaussian, at most an epsilon fraction 7 thrown out. And then all the remaining bad points are at most root log 1 over epsilon away from the mean. So by putting these two facts together in the right way, we have that the empirical mean of the remaining points satisfies exactly the guarantee we wanted. The estimate versus the true mean is epsilon root log 1 over epsilon. So this is great. This is why it works in one dimension. But what about in higher dimensions? Well, I'm not going to walk you through the calculation again, but you can see pretty much everywhere you're going to have the same, you're going to have this root d factor which shows up. And in particular, following through to the end, you're going to have exactly this root d factor that we were trying to avoid in the first place. So this is why this naive pruning method will not work in high dimensions. Let me try to actually pictorially show you what's going on. This is roughly what happens in 2 dimensions. Say you have your good points, and then you have your bad points, which are red ones. You can see that some of them are pretty far out, so maybe we can prune these ones. And anything that we don't prune is pretty close to the center, so it won't affect the mean much.
How do you decide what to prune?
Yeah, kind of basically. I mean, anything that looks far enough away, maybe these ones. I'm being a bit vague here, but the point is, even if you sort of remove everything on the outside, you'd be okay. But here in high dimensions, we could have the following picture. As you know, I'm sure that in high dimensions, samples from a Gaussian have this following sort of caricature. All the points are going to be very tightly concentrated at a radius root d away from the mean. So in other words, we're going to have this very thin shell where all the points lie. And you'll notice that any one of these outliers here that were put here, none of them individually looks like it doesn't belong. They look pretty feasible for all of them. So in other words, what I want to say here is, in aggregate, there's the fact that all of these points will move the mean, even though you can't remove any one individually. So any method that looks for outliers on an individual level will get stuck at this barrier of epsilon times square root d, just because of the fact that you can't remove any of these that line the shell individually. So this suggests the only method of attack is some method which looks for corruption on a more global level. And let me try to give you an illustration of what will happen when we look for corruption globally. This is the main idea behind our mean estimation algorithm. So it's the following. Suppose the corruption moves the mean, originally the mean is in the center here. But you notice we have all these points up and to the right. So in fact, the mean will be shifted something like this. Maybe not that far, but just to emphasize it for you here. Now what I claim, and what I'll try to prove for you in the next couple of slides, is the fact that they'll also shift the covariance matrix. So originally we have this nice circular covariance matrix, but you see now there's a lot of points up and to the right here. So the new covariance of the empirical of the data set will be something more like this. And since we know what the covariance is, then we can detect the fact that this is not the identity covariance. So that's the main intuition behind our mean estimation algorithm. So to be a bit more mathematical, this is the main lemma which is useful for us. The fact that if the empirical mean of the data set and the true mean differ in L2 distance by at least epsilon root log 1 over epsilon, then this will corrupt the spectral norm of the covariance matrix away from the identity by at least epsilon times log 1 over epsilon. And I'm going to spend a few minutes trying to sketch this proof for you. For simplicity, just so that I don't get my notation confused, we're going to consider the case where mu is equal to 0. Otherwise, I'll just be dragging them around all the way. So let's pretend 0 and show that this is what's going to happen. So we're going to pretend mu is 0, and then our data set S, we're going to divide this into the good points, that is, those which are uncorrupted, and the bad points, whatever the adversary is put in there. So the idea behind the proof goes roughly as follows. The first fact is that we know that the good points concentrate. Because they truly came from a Gaussian, they're going to concentrate around the true mean and covariance. So in particular, we have the following two guarantees. The expectation of the point from the true mean, from the true Gaussian, concentrate around the mean, which is 0, that is it now. And similarly, the covariance concentrates around the true covariance identity. Now, this might, for the very keen-eyed of you here, this might look a bit odd. Why do we have these root log 1 over epsilons? The reason is because I lied to you a bit here, or I was hiding something. S good is the remaining good points. So in particular, you originally had some sample from a Gaussian, but then the adversary took some away from you. So in particular, those could manifest, if you pick them right, by giving you these extra root log 1 over epsilon factors. But if that doesn't make sense, don't worry about it too much. I just want to say that the uncorrupted mean and covariance concentrate around the true value. So good, that's the first step. The second step is to observe that the empirical mean of the corrupted points must be far from 0. And why is that? Well, we know the overall mean of the data set is far from 0. And the fact that the good points are concentrated around 0, that implies that the points responsible for pulling us away from 0 are the bad points. They're not huge, but they still have some contribution. So we can say that the mean of the bad points is large. Good. The next thing is that because the mean of the bad points is large, this implies something about their covariance as well. This inequality may not be totally obvious to some of you, but let me just say that this is related to the idea that, if you consider the expectation of x squared versus the expectation of x and then square that quantity, this is the same generalization to that in higher dimensions. So in other words, we have that the covariance of the bad points is large. And the final step is just to break down what this quantity is. If you break this up into its component terms, roughly you can decompose this into contributions to the covariance by the good points and the bad points. So since we know that the covariance of the bad points is large, but the covariance of the good points is comparatively small, in other words, by putting these two facts together, we have that the overall covariance is large. This is roughly how the sketch of the proof works, and similarly for many of the other problems considered, it generally works by saying that the good points concentrate in a nice way, and then say that the bad points will corrupt whatever statistic we're looking at. So yeah, that's the idea behind the proof. And let me just go back to the lemma and really emphasize, if the mean is corrupted, it manifests in the covariance. I'll note that the first thing is something that we don't know, it's something we can check. But the latter is an easy-to-check condition. In particular, we can just take the SVD, the empirical covariance, and based on how large the singular values of this are, how large the eigenvalues are, then we can decide whether or not the data set is significantly corrupted. So this is the lemma that goes into our algorithm. How do we actually be algorithmic with this? We do the following filtering-based algorithm. So the first thing, like I said, we compute the empirical covariance and subtract out the identity. We compute the top eigenvalue eigenvector pair. And make a decision based on how large this eigenvalue is. If it's sufficiently large, maybe it should be an omega. If it's sufficiently large, then we know there's something funny going on. There's some bad points which are causing something to happen. And in fact, they'll be causing the action to happen in the top eigenvector of the data set. So let's take a look at this. This is basically a Gaussian projected to one dimension, which will be a Gaussian. But I told you some action is happening here, something interesting. So we're going to remove points in the tail where the data looks non-Gaussian. In particular, we have a very tight understanding of how the tail should look like if it were a Gaussian. And if you really squint at this, you'll notice that this looks kind of odd, right? In fact, this is I've injected some extra adversarial points here, and they're really manifesting by making the tail here look inflated. So what we can do is simply chop off the tail in this projection, and then and that'll remove some bad points. Otherwise, if we don't have a top eigenvalue which is large, then we know by the lemma in the previous slide that the empirical mean is close to the true mean, and we can just output the empirical mean. So this gives a very, while the proof is it can be complicated in some places, it's very simple to describe and in fact implement. You just simply do a single SVD calculation and you're good. So in fact, we have the following guarantee. Given an epsilon corrupted set of samples, after at most order d iterations of the filter, it'll output a mu hat with a guarantee that they're close to L2 distance. In practice, perhaps far fewer iterations are needed for this to converge, but in the worst case, I think this is what we can show.
So it's very long. We wanted to avoid this d.
Sorry, this is in terms of the runtime. We're okay with something, in particular, if you want to do these sort of computations in high dimensions, even looking at a single data point would require order d. So we're fine with the runtime being polynomial in d, but not exponential, and we're okay with the accuracy being independent of d. We do not want any d factors in the accuracy. So we can get both polynomial dimension and runtime and no dimension dependence in the accuracy. So that's pretty much the algorithm for unknown mean. I want to give you at least an idea of what happens in the Gaussian with the unknown covariance case. For example, how to robustly estimate this, where we know the mean, say it's zero mean, but we don't know the covariance. Like I said, it's a bit more complicated, but here's the main idea.
To come back to the known covariance case, you said in the beginning you want to forget the sampling noise. But if the size of your sample was comparable to the dimension, you couldn't.
Right. So
then this top eigenvalue, you would have to do a Wishart distribution, the transition at the edge of the Wishart.
So the number of samples we need is roughly d over epsilon squared, because this will cause the concentration we need. Like I said in the previous few slides, we need that the true mean and the empirical mean of the good points are concentrated. So roughly d over epsilon squared, and this is the best we can do even in the noiseless case, in the corruptionless case. So if you're below that, you might be out of luck. But yeah, so let me say a little bit about the covariance case. Like I mentioned, estimating the first moment, mu, requires looking at the second moment, the covariance. So naturally, if you want to estimate the second moment, what you have to do is look at the fourth moment of it, which has a neat structure. This is one way that some people describe it. I think the perspective I prefer is the following. When we want to estimate mu, we had to look at, is there a projection of the data which looks non-Gaussian, right? That's all really that an SVD or what a top eigenvalue computation does. It looks at the data set and tries to find, is there a projection where it looks funny? It looks like it has too much variance in some sense. And I want to note that this projection is equivalent to a degree 1 polynomial. It's just taking a sort of a linear function of the Gaussian sample projected. So the corresponding statement for estimating the covariance is there a degree 2 polynomial which looks non-Gaussian? So for a specific class of degree 2 polynomials, we can understand what the mean is, what the variance is if it was truly Gaussian, and we can also prove that things will, this type of polynomial will act up if we have corruptions. But that's all I want to say about covariance. It's, I think really the mean case has most of the ideas you need to apply this to a bunch of settings. So now we've got things which can handle unknown mean, and we can also handle unknown covariance, but how do you do both at the same time? And this might seem kind of tricky, but there's actually a simple trick which lets us do it easily. We want to estimate a general epsilon corrupted Gaussian, and we just do the following. We use what we call the doubling trick, or maybe halving trick. The fact that if you take two samples from a Gaussian, you take your difference, it'll now have zero mean. It'll maybe be more corrupted now, because either of the samples were corrupted, now your new sample is corrupted. But for the non-corrupted samples, you'll know that the mean is zero, and the covariance is now 2 sigma, something which is easy to understand. And at this point, we can estimate the covariance, sigma hat. Once we've estimated the covariance, now we can put the data points into approximate isotropic position. By that I mean basically just sort of rescale each data point appropriately by the now covariance which we know. And then this will give you something with identity covariance. But the mean is some transformation of this root. Note that now we have something which is O tilde of epsilon corrupted due to the log factors we accumulated in the covariance estimation step. But that's okay. We're still okay with these log factors.
What does O tilde mean?
Oh, O tilde means I'm hiding a log 1 over epsilon factor. Right. And so now that we have something with known covariance, we can just estimate the mu, the mean, sigma hat 1/2 times mu. And now the theorem that we concluded the fact that the Gaussian with these parameters is going to be close in L1 distance to the true distribution up to epsilon times log 3/2 1 over epsilon. So let me just note that that's because roughly we get an epsilon to log 1 over epsilon from this, and then multiplying how it interacts with the root log 1 over epsilon we get from mean estimation, it comes out to log to the 3/2. So that's basically what I want to say for the theory for this part. The natural question to wonder is, sorry,
It's wonderful.
sure. Yes.
So for the one case, you mentioned it's pretty much optimal. Is this pretty much optimal?
Yeah, that's what's something I'll get into in a few slides. I'll get back to that. The question I want to address first is, does this actually work? And I want to emphasize that this is actually an efficient implementable algorithm. I want to show you some plots comparing how it does with other things. So what we did was we compared our algorithm with other algorithms, including the work by Lyra and Paula, which is the blue line, ours is the black line. And then we compared with other sort of benchmark baselines which lose a dimension depending on factorial. So this is for mean just mean estimation. When we compare 100 to 400 dimensions, you can see that our L2 error is fairly minimal, while the classic benchmarks they're significantly larger. Whereas if you just compare ours with Lyra and Apollo, this is just zooming in on the previous picture, you can see we're still quite small in comparison to their result. So this shows the factor for unknown mean. And this is for unknown covariance. We have two experiments here. I can show you here's our filtering algorithm. It's the black line again, and LRD is the blue line. So in the isotropic case, where we have identity covariance, you can see we're pretty small. Weird things happen in low dimensions, but once we get to maybe sufficiently many dimensions, things are okay. And we're much smaller than the competition. But I think really the thing that stands out is in the skewed case, where we have, say, a highly elliptical Gaussian. In that case, you can see ours, which looks pretty much like zero. It's not quite zero, but it's just so small compared to the only comparison we could make, which was with LRD. And anything else you did with orders of magnitude that be through the roof right now. So this is really the only thing you can hope to do to get good estimation in the skewed case. So this is nice for synthetic data of this.
Just given how you generate how you modify the sample?
Yeah. Of course, you can imagine that there's some innocuous noise cases which would be that would be very, innocent into any distribution. But we found some which managed to truly show how much better ours does than other things. We couldn't really find any case where we did worse than anything else. Yes?
What are you going to compare with MSA?
I guess MS Smith.
Of the covariance matrix or the mean covariance classic?
Sure, perhaps
Covariance probability at least.
in yeah, I think perhaps that's something we might have configured that, I can't remember, but in these plots we plotted that. Yes?
So what's the variance of this curve?
This was averaged over several, maybe 100 iterations. So we found it was fairly stable in terms of the estimate. So that was it for synthetic data, but we also wanted to run it on some real data set, which caused us to revisit a classic experiment by November et al., which appeared in Nature in 2008, called the Genes Near Geography study. And let me describe what their experimental setup is. The researchers started with a high-dimensional data set, which is genetic information of individuals in Europe. So with this genetic information, what they did was they took each data point and labeled the data point with the individual's country of origin. For example, if an individual is from Spain, they would say that this is the annotate the data point, and in this picture they're marked blue, for example. And then they performed the following statistical experiment. They would take the singular value decomposition, they would take the top two principal components of their data set, and they would project onto the top two principal components. And that's exactly what they did and obtained this picture here, which you can see closely resembles the map of Europe. So to sort of repeat this, what they found was the two directions which explained most of the variation in genetic information seem to roughly correspond to the two directions in geographic space, that are latitude and longitude, thus giving rise to a catchphrase that genes near geography. So this is kind of neat and cute, but one thing I didn't tell you, and what was a little bit of a controversy, was the fact that they actually had to pre-process this data set. They had to remove people who might be outliers. For example, you could imagine if someone comes from Asia or Africa, then they might look genetically quite different. So they had to remove people who they considered to be immigrants. So this screams...
That's why they have so many Swiss.
I suppose the data set is probably biased in terms of who they
There are more Swiss than French. One population is 60-something million, the other is 7.
Yeah, I think so. Yeah, but the point is that they pruned it, and this screened out as a place where you want to do some sort of principled outlier detection. So we're still trying to get the original data set without their removals. It turns out to be very hard to get biological data, especially if you're a computer scientist and not an established biolab. So it's still in the process. So in the meantime, what we wanted to investigate is how does this do under synthetic noise? So what we did was we took this data set, which we had, which was already clean, then we added our own noise, and then tried to repeat the same experiment. That is, naively running principal component analysis and seeing what happens. And you can see Europe is destroyed. You can see that if you simply compute the top two principal components, they no longer contain any of the information that really encoded the map of Europe.
So, sorry, what did you do with that?
So what we did was we added outliers in some carefully chosen way, say, and we ran the same thing as before. We ran just computed the SVD and saw what the top.
So you added synthetic immigrants.
Precisely, yeah. We made up our own inputs with whatever biological data we wanted, yes. And you can see that in this case, especially dramatically, that the pruning projection, rather the projection you would get if you just use a naive pruning method would give you nothing.
Would I guess it's a little tricky, but would the noise added, would it make biological sense, or would it be like impossible to see a person?
That's a good question. I personally am not a biology expert, so I can almost guarantee you that what we added does not make biological sense. But I think it's a good idea. It's a good question whether maybe this model is naturally robust to biological outliers. So it's a question that I think deserves some inspection. So yeah, we tried to say a naive pruning projection, just moving points which go very far. But then we tried other things, including say a random sampling consensus method, which didn't really give much. Here's Shu, Karman, Sangabi. We ran their SMP for robust PCA. It still was not too effective, maybe a little bit better. But when you run our algorithm, you can see that the filter output is surprisingly close to the true PCA. and they both resemble the map of Europe. You might see some differences, for example. You'll notice that in the original data there were these 4 data points which seem to correspond to Turkey, but they're missing from ours. But that's sort of plausible in the sense that, if you only have 4 individuals, are they an outlier to the rest of the set or not? So perhaps you can say that ours is even more, I'm not going to make this claim, but maybe they were outliers to the rest of the data set in some sense. So I think this was a really fun thing to do. And I think this proves that our type of algorithm could be useful for exploratory data analysis. So that's it for experiments now. This is a question which has been asked once or twice before. Like I said, our accuracy is epsilon times log of 3/2 over epsilon. And the natural question is to wonder, can we get down to O epsilon? And interestingly, no, for computational reasons, in the following sense. If you want to remove these log factors, it seems like this requires exponential time in a certain computational model. That is, there's a well-known SQ learning model where you can only do specific types of queries for your data set. And it turns out that this seems to capture pretty much our algorithm and a lot of other natural algorithms you can consider. I'm not going to define it, but let's just say it's general enough to do a lot of things. And the nice thing about this model is that it's actually possible to prove computational lower bounds. In other words, if you want to get rid of these log factors in this, then it requires exponential time. And this was shown by some of our co-authors. But I think also interestingly is the fact that if you do a slightly weaker adversary, that is, before we had it that the adversary can delete and add an epsilon fraction of the data set, if instead he can only add a fraction of the data set, then you're golden. In particular, you can remove these log factors in either polynomial or quasi-polynomial time. And I think what's really neat is we're able to get all the way down to epsilon times square root 2 accuracy for the case of just unknown mean, compared with an epsilon information theoretic lower bound.
I don't understand what you mean by adding and deleting. I thought the adversary would just take things and move them around.
Precisely, but you can put pictures of the 2-step process where he first picks which points he's going to touch, then removes them, and then adds them.
Oh, I see.
But in particular, if he was only able to look at it and then when he adds them, then that's a slightly weaker model, which seems to actually have real differences. So yeah, we get this epsilon root 2. The root 2 is for a weird geometric fact, which I'm happy to talk about more offline and I think. And this was appeared in Soda this year. So one thing that also was asked is, can we go beyond Gaussian? Gaussian is a very strong assumption, and this has been studied for now lots of different classes. Everything in the sun, including say products, which is still nice, mixtures of Gaussian products, or products, sparse cases, and other things by a host of people. One thing I want to focus on is one result that we had, which was on bounded second moments, which I alluded to earlier, but I think this is a very general case, so I just want to highlight it. In this case, all we know is we have samples from a distribution with unknown mean and bounded covariance. And the theorem that we can prove is, given an epsilon covered set of samples from the distribution, we can estimate the mean in L2 distance up to sigma times square root epsilon. So you'll notice that I just want to mention this is similar spectral flavor to the Gaussian case. You essentially do the same algorithm. You find the direction which looks interesting, and then you sort of filter that direction in a specific sense. The technical differences are in the fact that we have weaker control over the details. Like for Gaussian, you know everything about it. You know exactly how well it's going to decay, whereas all you know about a distribution which has bounded second moments is the fact that you have Chebyshev inequality. That's essentially the main thing you know. And so this is why we get a root epsilon rather than this O tilde of epsilon. So good. That's everything I wanted to say about how we do mean estimation. Let me just take a little bit of time to tell you about how this can be applied for robust supervised learning. This is again with the same cast of characters, except it also includes Jacob Steinhardt now, who's just finishing up his PhD at Stanford. So the question on my mind now is, can we go beyond just robust statistics and also do more complicated objectives with corruption? So now we're going to have a setting where we have a distribution over xy pairs, where x are data points, but y are labels now. And we have some loss function, which is a function of x, y, the data point, the label, and also some parameter vector w. And so the problem we want to solve is, given an epsilon corrupted set of samples from D, find w which minimizes the expected loss when the sample is drawn from the distribution. This should be very natural to many of you, but just to illustrate how things fall into this, a linear regression has this loss function, the squared loss. SVMs have this loss function, and generalized regressions also fall into this. So this is a very, very broad problem of which we can study a lot. But let's, if you want to solve this in general, so for specific cases, there's a specific algorithm you can use, but in general, what are you going to do? You're of course going to run gradient descent, which looks something like this. Roughly you have a parameter vector, and then you subtract out some step size times, say, an average gradient of the losses. And that gives you a new parameter vector. And roughly why this works is because the goal is to follow the negative gradient of the objective function. And the empirical gradient works in the vanilla setting for the following reason, that, if you take the gradient of the objective function is equal in expectation to the gradient of the loss functions. So this is great in the vanilla setting when we don't have any corruptions. But what if some xi, yi pairs are corrupted? Then the issue is that, this equality doesn't necessarily hold, right? So the question I'm asking you is, how do we robustly estimate this quantity here? Does anyone have any ideas how we might do that? Well, if you've been paying attention to the first part of this talk, that's exactly the type of problem we've been solving. Roughly, gradient descent works by some mean estimation procedure, and we can sub in a robust mean estimation procedure here, and things work well. So we're going to have modified gradient descent, where now again we do take the previous parameter vector and take a step in the direction of gt, where now gt is a robust estimate of the gradient. And this can be done via the robust estimators from earlier. And in particular, you can bound them, if you have bounded moments of your data distribution, this will suffice to bound moments of the gradient of the loss function in many cases of interest. So let me just note that this is sort of like what the algorithm at this point is roughly, take a step in gradient descent, then run our filter, compute the mean, and then you have an approximate estimate of the mean, then you take another step, then you run our filter again, and then run it again. This is kind of very costly. So this works in theory, but in practice, what's better is, you run vanilla gradient descent to convergence, then you run our filter, and you're either going to find no outliers, and then you're good, or you find some outliers, you can remove them, and then run a gradient descent again. And this turned out to require far fewer running with our filter, maybe 2 or 3 or 4. So good. And this was a paper, a preprint we put up this year. I should note that others have also tried to recently port these ideas from robust estimation in order to do this type of supervised learning. Just to show you a flavor of one theorem statement, suppose we have that the loss function is convex, and we know that the covariance of the gradients is bounded, which, as I mentioned, is the case we can do in any if the loss function is not too crazy, and some mild condition on D, then our algorithm, which we call sever, outputs a parameter vector which is accurate up to the sigma times square root epsilon, which you might recognize from the second moment filter.
But here too, you need the size of the sample to be big enough?
Yeah, precisely.
Because otherwise, even the usual gradient descent won't work.
Exactly. For this one, we still need in this case, we haven't optimized the sample complexity much. It's a bit more costly than if there was no noise, but things are generally okay. But yeah, again, if you don't have like polynomial is what I want, maybe like up by a quadratic factor. But in practice, it seems to work still pretty well compared to.
So you need a sample size which is what compared to the dimension?
It varies depending on the specific problem. Say the worst bound in our paper that we have is say d to the 5 in very worst case. But yeah, it varies. And in practice, it seems like it's better. I'm running out of time, so I'll just flash through some things. Our algorithm works in practice without implementation. So yeah, in conclusion, I just wanted to say that today I talked about methods for robust estimation, which are applicable in many settings, in both supervised and unsupervised settings for a variety of distributions. And it seems like there's a lot that we can do here. They're computationally efficient, sample efficient, accurate in high dimensions, and I think excitingly realizable. These may actually be applicable. But there's still a lot to explore, and I hope this encourages you, some of you, to look into this area. Thanks.
Any more questions?
So in the heavy tail case, when you don't have Gaussians, we get the truth epsilon. Do you think it's possible to improve that epsilon if you use, instead of as a sample, maybe use one of these sub-Gaussian robust geometric medium mediators?
I do not believe, I think like actually this is the information theoretic optimal, roughly for the sense that, you know, an adversary could move all your data out to a specific, he could corrupt it in a way which basically makes the Chebyshev inequality tight and also looks plausible, if that makes sense. It still satisfies the second moment condition, but you don't really know which one you were looking at in the first place.
But that, I think that argument only works if you insist if you're using the empirical mean.
Yeah.
Much better estimators.
Right.
So,
I have to think of the specific thing, but I think you can show an information theoretical workaround in the sense that you can construct two different distributions which are both epsilon corruptions away from each other. So you don't know which one you're looking at in the first place, but they in fact are true, their means of these distributions are separated. Yes?
What happens for small epsilon?
Sorry?
Should epsilon very small?
Yeah, this works for epsilon very small in the sense that
Because our is when they were small different.
I guess definitely for constant ones, any small constant.
For one to be dependent and like for epsilon which can be a small portion, like n to the power it's n to the power u with small something.
Yeah, that's a good question. I'm not sure about that scenario. I can't make any claims about that. Yes?
So this model seems to be the malicious noise is stronger than the usual agnostic. I mean, if your algorithm here works, it should work in the agnostic setting as well. So I'm asking if you want to learn a Gaussian in the agnostic setting, we can still use your algorithm, and it will be computationally, presumably efficient. How does it compare computationally with the other recent robust, agnostic learning methods for Gaussians?
Yeah, I guess you're saying the agnostic setting where perhaps, you know, we have something which is not exactly Gaussian. There's also called the Hubert contamination model, where you have like 90% of your data from, say, true Gaussian, but 10% is sampled from some other distribution. As far as I know, there was nothing that sort of works in high dimensions for this type of setting either. So ours encompasses that setting, at least for the unsupervised setting, nothing was known for these.
Not this model, so it's not Hubert's model. It's just we assume that the data is coming not from exactly Gaussian, but a distribution that is, let's say, epsilon in L1 distance to the Gaussian. But it is IID, it's nice. So your model is...
it's more generally, yeah. And I don't know if any, maybe a misunderstanding, but I don't know results for, say, unsupervised learning for Gaussians in high dimensions.
There is another notion of depth that is called spherical depth. I don't know if you are aware of it. That is computationally work because it's n squared, irrespectively of the dimension, and it's easy to calculate. You just take, for each pair of points in the sample, you take the ball with this diameter, and you count how many points are in there.
I see.
And the center is the point that maximizes this. And this you can run it n squared, n cubed, because you have to make a inner product and then take every pair.
Right, I see. There seems to be computational efficient, yeah.
Does not require any solution underlying.
I guess
Well, you need that the center will be very well defined. Something like
right. I think it's not 100% clear to me whether this gives something which is accurate or not, so it would have to be, the analysis would have to be done. But it's an interesting direction to wonder if this will work out. Yeah, that'd be handy. Thank you.
Any questions? Okay, thank you very much, Gautam.